I don't even know what the hell just happened. This thing was like getting clunky, and I was like, what the frick is going on? Why is this moving like this? It was just very laggy, and I was like, what the heck? And I tried to troubleshoot it, and then it troubleshot me, I guess. I don't know. But we're good, I guess. I had to start over, but that's fine. I'll just... Oh, IBM's Qiskit is doing their quantum computer seminar series. So I'm actually going to listen to that too. Hopefully I don't get too distracted, but... Actually, I listen to it on my phone since my headphones are connected to my phone. I think that just makes more sense. And then you know what? I'm not going to lie. I think there's basketball games on tomorrow, or today. Dude, my freaking bracket it's screwed. Houston lost. I had Houston winning it all, and they lost. My bracket is screwed. Oh, Notre Dame plays at 2:30? Bro, why would they do that? 10 p.m.? Like I don't have a bedtime. Like, I don't have a bedtime. But it's okay. I have UConn, of course, winning the women's bracket. Or Texas, I'm not going to lie. Notre Dame and Vanderbilt should be very good, though. That's at 2:30, dude. That's fine. I'll figure it out. Yeah, bro. All right, let me listen to this. Okay. Bro, I was locked in. Hey, Mitoli. I missed him, but yeah, bro, freaking, oh, dumbass equilibrium. This is, don't even get me started. Don't even get me started. Okay, here's where my frustration is coming in. When I'm adding two COs, is this 2 CO or does this just become 1 CO2? Because if it becomes 1 CO2, these cancel, and then we're just left with H2O, H2, CHO3. I have no clue. I don't know. And I'm thinking about it, but it's not clicking. I'm not gonna lie. It's not clicking. Because the goal is to get this, and we already have H2O. Sorry, that was a crazy line. We already have this. But why is this over here? That's funky. Because I'm supposed to put it in terms, I'm expressing the first in terms of the second and the third. I might have to come back to this one. Yeah. I don't know what the hell is going on there. But it's fine. Okay. Now we're doing it in terms of pressure. All right. All right, I'm back in that mode. Also, anytime I can practice writing the equilibrium constant. Wait. Oh, I thought I had a sneeze. I'll practice it. I probably have about an hour left of studying, not gonna lie. Because I don't want to like study and try and watch the game at the same time. Like it's not gonna work. But my minimum like discipline is I at least want to stream every day for like 2 hours. I feel like that's calm. But we'll see. Okay, so now I would express this as KC because it's the concentration constant. And it's expressed in molality. Which is moles per liter. I don't know why I'm doing this. It's kind of fun though. Okay. Okay. Yeah, I think if I remember, the formula is like Kp is equal to Kc RTN, right? Yeah. Change in N. Where N is like the number of moles. Okay, now I feel super confident because now we're basically at the point where I am in class. So that's good. That's good stuff. So then let me Oh, okay. I was like, where did this PA come from? But this makes sense. So now now Kp would just be written as the partial pressure of SO2, because this is the number of moles, times the partial pressure of O2. And these are the products. And then we would have the partial pressure of SO3. And these are the number of moles and then we have the relation between Kp and Kc. Since the partial pressure of a gas in atmospheres is not the same, and then this is where when they're talking about deriving some sort of relationship, as long as the gases are behaving ideally between the two constants, this is where we start getting our Kp equals Kc RT change in N. This is just an excuse for me to write the equation again, by the way. Oh my gosh. All right, let me lock in. All right, the concentration of an ideal gas A is the number of moles of A over the volume in liters, and this is the concentration of an ideal gas. From ideal gas law, Pivnert, we can relate the number of moles of A over V to the partial pressures of A as follows. We're basically doing Pivnert, but the pressure is in regards to this concentration. Okay, and then since the concentration A is just equal to the number of moles of A divided by the volume, we can write it as this. Now consider the following equilibrium condition, which if this was in terms of concentration, we would have D, C, B, B. But if this is in terms of partial pressures, this would be partial pressure of D, to D, the partial pressure of C, there's C. Whoopsie. Respect to A. All right, and then according to the law of mass action, we would write this as this. Substituting X is equal to partial pressure of X divided by RT for each concentration term. We would get this beautiful mess. And this is just the change in N that they're talking about. The change in moles. These are just change in N and moles. Yeah, I think you can hear that. Can you hear my Beethoven? That's so funny, bro. Oh, and they want me to find KC. Well, if we know KP is equal to KC RT change in N, over here we have N equals 3, N equals 2, 2 minus 3, change in N is equal to a negative 1. So then our temperature is going to be like, what, 293.15, because it's usually 273, no, 298. And then our change in N is going to be equal to a negative 1. And then R is like 0.08206. I think this is what it is. And that's pretty much it. Let me just plug all this stuff in. So then getting rid of this and writing what it actually is, we would have like, what is KP? 2.2, 10 to the 12th. I'm trying not to look at the thing. So we would have 2.2, 10 to the 12th equals some KC times 0.08206 times 29815 raised to the negative 1. Actually, I'm going to put this in brackets. All of this raised to some negative 1, which is basically like putting this over 1. But so then we basically get that KC. I'm just going to do the math. I was going to write it all out, but no, I don't want to do that. And then take this and to the negative 1, and then 2.2 e to the 12th divided by, let me make sure it was e to the 12th. Yeah. KC is 5.3, let's call it 5.4, 10 to the 13th. Yeah. Okay. What is the value of KP? So temperature, moles. So what do we've got? We've got 2. Perfect. All right, now we're looking at units of K. Wow, this mic is like super sensitive. I just noticed that. I believe I understand what they're trying to say, but we'll see. Under which circumstances are K, P, and KC equal? If A plus B equals C plus D. Oh, this is true. Because then this would assume that the change in N would be equal to 0, which would mean that KP would be equal to KC. If the reaction is reversible, what the hell does that have to do with anything? I don't know. If the equilibrium constant is small, yeah, I think this is just A, B, or C. Okay. Do you say heterogeneous or heterogeneous? Jeez. Okay. We're actually doing pretty good, not gonna lie. I think we're almost at the end, low key. Yeah. Yeah, we are. So there's the self-assessment quiz. So we have this chapter, then we have I don't know, his principle. Okay. Heterogeneous equilibrium. Mind you, I still have chapters 18 and 20, which my homework is due on. Which I have no clue when that's due. And I have a test due on Monday. Oh, no, never mind. We're calm. My homework isn't due till... What the freak? That's probably a typo, right? April 20th? I think that might be a typo. But we'll see. Then again, I am, like, actually catching up for once in my life. Not being behind and such. Okay, many chemical reactions involve pure solids or pure liquids. We might expect the expression for the equilibrium to be... That's exactly what I thought it was going to be. Since carbon is a solid, its concentration is constant. Okay, so its concentration therefore depends only on its density, which is constant as long as some solid is present. So then we would just omit it. We would omit the solid. Okay. Okay, when the solid is present, we can omit it from the Kc equation. Similarly, the concentration of a pure liquid doesn't change, but you would think that pure liquid, because they're liquids, their concentration... No, they're also excluded. So what am I looking for here? G's. These are... I hope I just spelled omitted correctly. Same thing here. But these are aqueous, so these are solutions. Okay. That's fine. So here, this would be, our KC would just be CO2. CO. And this would be omitted. Okay. There's no way you can hear that outside. That's so funny, bro. Okay, for this problem, I'm almost like, do I just assume this is gonna be 1.00? Like, let me see. That's what I did. I got that. Dude, I think I'm getting sick. Oh, isn't it? It's sprained. I don't have. Sorry, I don't have allergies. But. Oh, man. Okay, let me see. Yeah, I think. Oh, so it would just be a -2 times that value. So we would just do a -2, because that's the constant. Or why did I put a -2? 2 times. But you see how. Oh, wait, no, it's positive. Okay, good. Which is going to be 70. So then the change in this is just going to be 0.30. And we kind of know that the total should be 1.5, right? Or how does this work? Why is this a -2? Hold on, I gotta blow my nose. This is getting ridiculous. I got a little sidetracked. But yeah, why is this negative? Let me make sure I set it up right. Okay, I did. I should fact check that. They just love to like do landscaping over here. I hope this is correct, but I goofed a bit because the first time around I was like, oh, I'm just making my own formula, but it was actually based off of these that they initially gave us. So that was fun. So I had to go back and do that. And the only way I figured that out is because it was, it just referenced the example and says it's now carried out to a different temperature and with different initial conditions. Okay, and then now we start getting into the reaction quotient, which is also pretty important. This is, I remember this from the homework, so I don't know how to do it, but I remember this was definitely on the homework. It's literally what we've been doing this whole time. Or am I tripping? This makes sense. This is the same in math. If your denominator is bigger than your numerator, it approaches 0. But this one, containing only products, I mean, this makes sense too. It can get infinitely large. That makes sense. Okay. Oops. Whoa. What in the world is this? Oh, I see. When Q is greater than K, the reaction runs to the left. And if Q is less than K, the reaction runs to the right. And if Q is equal to K, then the reaction is at equilibrium. Same thing. Q is less than, so the reaction is going to run to the right. Q is greater than, reaction runs to the left, and here we see that it's at equilibrium. Okay, so this is less than. So here we would have to calculate Q, yeah, and C. So here Q is, but where are we getting the values from? Oh, I see, right here. Okay, and then they already got that it's going to be 10.8. Now, we know that KP, so we see here that Q is less than K, so the reaction is going to run to the right. Yeah. Okay. See, now this is different because now we're given KC, and that would mean we have to calculate KP. But if we're not given a temperature, oh, it's just at some temperature. So then maybe it doesn't matter. Maybe K is just K regardless. So then Q is equal to and this is what our Q would be. And then it says here, or excuse me, our QC. And our KC is really 0.00585. So basically our QC is greater than our KC, so the reaction runs to the left. Let me write this down too. So it's less than K, so reaction runs to the this is chemistry. Bruh. This is chemistry. Specifically, I don't even know what the hell, but it's equilibriums. On the left over here though, it's proofs, which is what I need to start doing in a second. But it's proofs, set theory, predicates, propositions, truth tables, set logic, empty sets, elements of sets, elements inside of a set, intersections, unions. So I think this is subset. So just kidding. What did I just say? toward the products? No, towards the reactants. This one is the reaction that runs towards the products. Right, because it's less than, yeah. Okay, and then Q here is going to be the partial pressure of NO2 squared over the partial pressure of N2O4, which is going to be equal to I guess I'm just using the same values from up here. So 0.0255. Is this literally the same problem? Yeah. So my answer is almost the same. But here we see that Kp is actually equal to 0.15, which is greater than Q. So then we know that the reaction is going to move to the left. Yeah. It'll proceed to the left. Okay. Honestly, that was pretty much all I kind of had to do today for chem, because I might stop here because now we're getting into using variables instead of given concentrations. And then, or should I just come back? What is this, 15.8? I might just come back to this. Yeah, I think I'll just come back to that section. Let me see if oh no, I've got like 20 some more minutes before the game starts. All right, bet. Let me see. Okay, so I'm going to skip 15.8 and learn about the principle. I'll come back to this. There's a lot of problems on the homework talking about this specifically. Like fill in the blanks, it was drag and drops, just about if we raised or increased the concentration of this reactant or this product, or we increased the volume of this reactant, then how would the equilibrium change? Which way would the reactants and or products shift? There's actually a lot of, I want to say like 50% of my homework was questions like that actually. Oh, that was pretty simple. It makes sense though. It's the chemical equation doesn't want to be unbalanced, so it's going to do everything in its power to get back to equilibrium. So if we add a concentration to the products, or if we increase the concentration of one of the products in the products, the whole thing is going to shift to the left because it wants to stay and remain in equilibrium. Vice versa, if we did something to the reactants, then it'll shift to the right because it wants to remain in equilibrium. By it, I mean the chemical equation, by the way. So like here, if we add an addition, wow. If we add an additional CO2 to the reaction mixture, then the whole thing will shift left. It's going to shift to the left towards the reactants. God bless me. Okay, vice versa. If we added additional CO3, what is that, like calcium carbonate? Maybe. Then the reaction, it will shift to the right. And then this also goes back to that idea of when Q is greater than K and when Q is less than K. Yep, shift to the left and, oh, it's a solid. I didn't even see that. There's no effect. Oh, that's on me. That's so real. Actually, I'm just gonna say I was wrong. Oh my gosh. I love a good long. You know what they should do? I don't know if they do this though, where you can like put like a bell or like, I don't know, some sort of notification. If someone like hops in the chat and says something, they probably have that. They probably have that. They probably got that. Because the more and more I think about it, like I'm just locked in, and so I don't see chat because I'm locked in. I'm locked in, right? But like if I heard like a, I don't know, ding, I'd be like, oh. But see, then I feel like as I grow, like this channel is gonna get annoying. I'd probably turn it off because then it's just gonna be ding, 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 ding. Like I'm not gonna be able to focus. Okay, I think I'm gonna stop here because this is kind of the point I wanted to get to. And then we get to, or should I just tough it out and go through this 15.9? And I'll just push through. But if volume changes, then doesn't that decrease concentration? Does that make sense? Because now it's almost like having salt in water. If we add more water, then the salt is kind of spread out over more area. Pressure and volume are inversely related. Decrease in volume is an increase in pressure, and increase in volume is a decrease in pressure. This makes sense. Like think about people who deep sea dive. The deeper that they go in the water, the more the pressure kind of, is it that pressure increases or that pressure decreases the deeper you go? I think pressure increases. Oh my gosh. Oh man. Yeah, this makes sense. There's more stuff down here, which I will read later. Maybe. Okay, so, yeah, this is an increase in pressure. So then the reaction's going to shift to the right toward the side with fewer moles of gas particles, but on a decrease in pressure, the reaction's going to shift to the left. The effects of temperature. Yeah, I noticed this. No matter what the temperature was, the equilibrium constant did not change. It was in one of those tables. This makes sense. Like all the reaction wants is for Q to equal to K, which is equilibrium. Anything that disturbs that, it just tries to, I guess, recalibrate. I'm interested to see how this is going to work, because with reactions, yes, it's positive change in H and it absorbs heat, but the concentration tends to be negative. I don't know if that has anything to do with it, but... Why does the value of the equilibrium constant decrease? If it shifts towards the left, the constant would decrease, meaning that the numerator and the denominator, meaning the denominator is greater than the numerator, meaning the reactants are greater than the products. I think that's how I have to think of this. So if this is endothermic, so that means it's going to absorb heat, which means this is a positive change in H in the reactants. So this is basically like saying plus heat over here. And we're going to raise the temperature, which means if the temperature is being raised, the reaction is going to shift to the right. Temperature is being raised, reaction shifts to the towards the products. So then when this happens, now we have a If we're shifting more to the right, the products are getting greater. I think this is why K is increasing. But then the decrease of the temperature, yeah. But with a decrease in temperature, the reaction is going to shift to the left toward the reactants, which would mean that for K being numerator over denominator, we would have shifting more towards the left, which is the numerator. Numerator is going to be greater than the denominator, which means that K is going to be decreasing. Okay. That's endothermic. Okay. That was definitely not fun. I'm starting to enjoy stuff like this more though, just because it has math in it, and I'm like, oh well, you know, I like math regardless, so whatever. All right. We did a good bit though. And there's the self-assessment quiz. Okay. Now I'll look at this. Briefly. Yeah. Do I want to do this? Yeah, I think that makes it easier. Did it though? Yeah. Okay. Yeah. All right, now, oh, I was gonna look at this book, because this is how I was, oh wait, I'm a Dinkleberry, I already have this. It's fine.
Thank you so much. Welcome to 6-1200. 6120, I don't know how you want to pronounce it. Anything goes. Either way, welcome. Really looking forward to a great semester with all of you. So a couple salient points. Structure-wise, schedule-wise, we have lectures on Tuesday, Thursday, 2:30 to 4, which I suppose you know if you're here in person. We have recitations on Wednesdays and Fridays. We do take attendance at recitations. It's worth 10% of your grade, so we highly recommend that you go, both for your grade and also it's some of the most useful time that you'll have this semester.
Okay, so I think how I'm gonna do this. Why does it not fill the white space? Is it just me? Oh my lord. Alright, we're just gonna go through this briefly. Oh, I like when it has the tail on it. That's so cool. Okay, so, dude. Alright, okay, so we're looking, I have no clue what a predicate is. This is gonna be fun. Oh, that's what I meant to say. Should I go through the textbook first? Nah. Nah. If I get stuck, I'll look at the textbook. This is just the lecture too. This isn't even the P set. After I finish this lecture, we'll do lecture 2. And I think I'm just gonna like watch the game over here on the side, low key. Oh, is there gonna be? Oh, I think there's gonna be audio. I mean, duh, it's gonna be audio. But it's fine. I'm just gonna quietly, independently do this. Oh, it hasn't even started yet. All right, bet. I'm thinking that PSET 1, let me just look at the calendar. Don't they have like a, okay, yeah. Lecture 1, lecture 2, lecture 3, and lecture 4. So now I'm thinking, this is why I kind of wish there was like a calendar, low-key. Because at what point do I start doing the problem set? We'll just do it like this. I'll do lecture. Why does it look like that? Bruh. I think I gotta get a new renderer for graphics. Is that even possible to get a new renderer? Yeah, I low-key want to get a new one. Cause this. Okay. Okay, this is just random MIT stuff. Random MIT stuff. This is real though. As soon as you look at the solution, of course you're gonna be like, oh, that makes so much sense. That's so trivial. Like, oh, that's so elementary. That makes so much sense. But like, it's if it was, then you would have pieced it together. If it was that trivial. Okay, proofs. What is a proof? A method of ascertaining the truth. Okay. Experiment, observations, sampling, statistics, legal, public opinion, business, school, religion, inner conviction. In mathematics, a mathematical proof is a verification of a proposition by a chain of logical deductions from a base set of axioms. I look, you want to change this color to like something brighter. I actually have no clue what an axiom is. Is that crazy work? I've heard of it, of course, but like, what is an axiom? The foundational, axioms or postulates. I've heard of these names. So, but how can it be accepted as true without proof? Okay, I think the game's on now. Bro, I knew it was gonna be loud. Damn. Sorry. That was a horrible shot. That was a horrible freaking shot. Alright. I guess I'll go look in the mathematics section to figure out what the frickin' axiom is. An axiom, postulate, or an assumption is a statement that is taken to be true. Okay. Deductive rules. They use the word logical deductions. But here, this logical deductions can also be seen as rules of inference, ways of deriving conclusions from premises. Basically. Okay, so over the next few lectures, we will delve into predicate logic, also called first order logic. I've never heard of that before. So proposition is a statement that is either true or false. A predicate is a proposition whose truth depends on variables. So the way that I see this is there is propositions, which can be true or false. And then there are predicates whose true or false depends on variables. Or I could say they're variably dependent, but variable dependent. Proposition 2 plus 3 equals 5, this is true. 2 plus 3 equals 6, this is false. For all n's included in, oh gosh, what is this, like a real number? Oh my gosh, what is that? That's, consult the book. Actually, what would that be in? That'd be in, I mean, it doesn't matter too much, but I do want to know what it means. Natural numbers, isn't it? Yeah, the set of all natural the set of all natural numbers. I'll keep this right here. This is the real analysis lifesaver. I think this is for all. For all. I probably should have looked in there too. Okay, so yeah, it is for all. Universal quantifier. Followed by the predicate, which we know there's the predicate, whose truth depends on variables. It's 4 to 5 right now, my lord. Okay, then there's in elements of a set, and then there's the natural numbers, the set of non-negative integers, 0, 1, 2, on and on and on. To see if preposition 3 is true or false, we need to know whether the predicate, which is the, yes, I'm going to continuously write it every single time. This is kind of how I learn. The statement the predicate has to be, well, we need to determine whether the predicate is true for each value of n. So we write down multiple values of n and we test them. And this is a truth table? Or no, I don't think so. So we look at for n that equals 0, and then we apply it to our predicate. So we have a, I guess we can call this guessed values, because they're not given. These are just things that we're trying. So we're checking, I guess we'll call this choices of n. This is our choices of n. This is our predicate statement, and then this is what we are trying to evaluate. Is it prime or not? Okay, so I kind of want to do this in a expands table. So when we have, so when n equals ... 0, we get 0 squared plus 0 plus 41, 41. 1 plus 1 plus 41, 43. 2, we get 4 plus 2 plus 41, 47. 3, we get 9 plus 3, whoopsie, plus 41, 53. Okay, yeah, that's right. 4 gives us 16. 4. I keep drawing my arrow early. 41, which gives us 61. 5. 25, 5, 41, 71, and then so on and so forth, which is kind of what they said, or what they're, dude, so on and so forth. And then we evaluate it. Is this prime? What is a prime number? Prime number is like the only factors is the number itself and 1. I think that's what makes a number prime. Right? I think so. Prime numbers, integers, evens, odds. I've noticed a lot of proof, a lot of like beginner proof questions ask about those. It would probably be in numbers, and then we would go to prime, because that's rational, square root, number theory. I should have just typed it in. A natural number greater than one that has exactly two distinct positive divisors, one in itself. What did I say? That was divisors. I said what? Factors. That's probably why we defined it to be elements within the set of natural numbers. That's a condition for primes. Okay, but if n is equal to 41, then n squared plus n. So instead of being 1 in itself, now the two distinct potential divisors become, I'm just going to say factors because I like that better because it's what it can be broken into, which is 43 by 41. In mathematics, we call this a proof by example, which is not a valid proof. Let me highlight that in red. Okay, so some propositions in number theory are even more devious. So again, we know propositions are, these propositions can be evaluated with true or false statements. Okay, we are getting our behinds whooped right now. It's 11 to 5. It's actually not bad. It's actually not bad. Proposition 4, false. A to the fourth plus B to the fourth plus C to the fourth equals D to the fourth has no positive integer solution. This is basically saying there is no positive integer in when substituted into the equation or the predicate that will yield true, is basically what they're saying. We've not scored in the last 5 minutes, and we just traveled. Oh my lord. It's getting ugly. It's getting ugly. It's fine. Okay, so conjectured by Euler in 1769, ultimately disproved by no clue who that is. Oh, look him up. The solution is A would be, oh, so these can be different. So see, I thought that this would actually be the same number. That's why I was like, oh, that kind of makes sense though. So the solution, so the proposition 5, For all A, B, C, and D's in the set of natural numbers, positive natural numbers, A plus B plus C all to the fourth power does equal D to the fourth. Oh, wait, no, it's not natural numbers. I'm sorry, this is integers. This is how I envision the problem being, I guess, written, spoken, either or. So, yeah. I could be wrong. And then here's the chapter on propositions and predicates. Whoa, they greatly simplified this in the lecture notes, because what the hell? Okay. And I gotta figure out. Okay, so then proposition 6. Given 313 times x cubed plus y cubed equals z cubed, it has no positive integer solution. Smallest counterexample has over 1,000 digits. Holy moly. That's kind of insane. So there is a counterexample, just the solution is, I don't know if I would say like it's far out, but the fact that the solution is about 1,000 digit numbers, it's kind of crazy. Or that the counterexample has over 1,000 digits is kind of crazy. Oh, and then there's Goldbach's conjecture. Every even number greater than 2 is the sum of 2 primes. So every even number greater than 2, so this would be like 4, is the sum of 2 primes. Isn't 2 prime? Yeah, because then 2 is just itself and 1. And then 6 is 3 and 2, which is just 3 and 1, 2 and 1. We could go on forever, I'm sure, which is exactly what this says. It's unknown whether this is true or false. It's true for every even number ever checked. Math community generally believes this is true. and seems pretty difficult. It's listed as one of the great unsolved mysteries on the front page of the Boston Globe. All right, it's useful to construct new propositions by combining existing ones. So A and B, both A and B to be true. I know about this. Now we're getting into, I guess, basic set theory notation. A or B, at least A or B is true. This is inclusive, or meaning it's also fine for A and B to both be true. Not A. This is how I've seen it written. A is false. Truth tables. So, I love truth tables. If A is true, then not A is false, which says that A is false, which is true. And it makes sense because A is true. But if A is false, then not A is true, because then it's true that A is false. It really screws your brain up, honestly. I'm not gonna lie. Like, thinking about this screws your brain up. Not gonna lie. This is probably some of the most difficult parts. If A is true and B is true. See, when you look at it like this, it's like, what the frick? But when you think about it, what was an example I saw? I took like a Harvard, that sounds so weird, but Harvard posted like one of their math lectures from one of their proofs courses, and I was like watching it, and instead of explaining it like this, he explained it as A is it was like a bicycle has 2 wheels, and B was something like, if it doesn't have 2 wheels, it's not a bicycle. I think this was something else though, I could be wrong. I think this is like proof by contradiction. But if A is true and B is true, A and B is true. A or B is also true, because this requires us to have one or the other, or both. Both is also an option. Let me think. Now, if one is false, then this is also fine, but it's fine. But then that means it only applies to A or B, where it's, again, one or the other. But it can't be A and B, because this requires both to be true. And it just doesn't work like that. And then if they're both false, then A and B is also false, and A or B is false, because it's not one or the other, and it's not both. Yeah. See, like, it's chicken or pasta. So you can choose chicken, or you can choose pasta. I mean, you can't choose steak, because steak would be this last row if you chose steak, because we don't have that. It's just chicken or pasta. Okay, so yeah, you can't do both. Coffee or tea. Okay, so you can have coffee or tea. You can say just coffee, just tea, or neither, but you can't have both since you only get one mug. This is different too. It depends on, basically what I'm getting from this is it's situational, and it depends. It all depends. Cream or sugar? Oh yeah, A implies B. A implies B. If A is true, then B is true, then A implies B is true. If A is true, but B is false, then A cannot imply B. If A is not true, but B is true, then A implying B is true. But if A is false and B is false, then A implies B is also true. Why is I don't know which one of these I'm more confused about. If A is true but B is false, then A implying B is false. But if A is false and B is true, then A implying B is true. If Wednesday, wear pink. Wednesday implies pink. Oh. Which one are they talking about? This one. So if it's not Wednesday, you can still wear pink. Okay. Wearing pink on Wednesday doesn't violate the rule. That makes sense. That's what I was talking about, contrapositive. Yeah, I'm definitely gonna need to review section 5, because what the frick was that? Okay, now we're getting into sets. I've never seen this before, where a set contains other sets as elements. Oh wait, yeah. Okay, holy moly. Yeah, I have seen that. I think that's just, is that a subset? Where a set contains other sets as elements? There's no such thing as duplicates. That would be a multi-set. Okay, and then the order of elements doesn't matter as well. Six is in the set A. Is 1, 2 in the set A? No. Oh wait, set A has 4 elements and B has 3. Is 6 in, we wrote that 6 is in A, is 1, 2 in A, is 3, 4 in B. Sets can be subsets of each other, means all elements of S are also elements of T. So this could be written like this, where this is S, this is T. All elements of S are also elements of T. Or at least that's how I think about it. And this is a subset. Okay, so is 1, 2 a subset of A? Is 0, 1, 2, 6 in a subset of A? Oh, I was like, where are we getting A and B and all this from? But we defined A to be this. So now we're using predicates or statements whose truth depends on variables to specify a subset. So this says that n is within the set of natural numbers, then is prime. Oh gosh. Okay. So yeah, and then you can combine sets into other sets, intersections and unions. Intersect or find where A intersects B, or we can union A, union B. Take the difference of sets A minus B, the set of elements that are in A that are not in B. Ordered tuples written with parentheses is not the same as this. 2.160 is identification, estimation, learning, and mechanical engineering. Duplicates are also fine. 61200. Union intersection don't make sense for ordered tuples. Axioms. Second component of a proof is the set of axioms on which it's based. An axiom is a proposition that is assumed to be true. You may have heard, don't make assumptions in math. You must make assumptions. Key is to state them up front. Okay, so if A is equal to B and B is equal to C, then A is equal to C. You've got a point. You've got a point. Okay. Given a line L and a point P, which is not on L, there's exactly one line through P parallel to L. So given this line L and a point P, there is at least one line that goes through like this. There is no line through P parallel to L. This is true. You could do something like this. It's not parallel, but it goes through. There are infinitely many lines. This is true. I don't know if that one's true. There are infinitely many lines through P that are parallel to L. I don't know if that one would actually be true or not. So, anyone who agrees with your axioms must accept theorems derived from them. Lines are just different objects in these three worlds. There is no correct set of axioms, but we would at least like. Definition 5, a set of axioms is consistent if no proposition can be both proved and disproved. Okay, and then definition 6, a set of axioms is complete if every proposition can either be proved or disproved. So, consistent versus complete. Consistent is the proposition cannot be proved or disproved, whereas complete is if every proposition can be either proved or disproved. It's not ambiguous. No set of axioms is both complete and consistent. Oh. So it's one or the other. Either your propositions can be proved and disproved, meaning they're complete, or they cannot be proved, or not all of them can be proved or disproved, meaning they are consistent. But no set of axioms is both complete and consistent. But this is proved by Kurt in the 1930s. If you want consistency, which is necessary, then there are true statements that cannot be proved. Maybe Goldbach's conjecture is true, but there is no proof. And that's lecture 1. That wasn't bad. But definitely gonna have to come back to section. I understood everything but implication. And I understood this implication section, but it was really once we got like here and below. Like here and below is where I was like, okay. the hell is going on. So I'm gonna have to go through that. Yeah. Yeah. Okay. Now I just want to do physics, I'm not gonna lie. Did a whole bunch of math. I feel like I deserve it. I also need to start doing some classical mechanics too. Yeah. I have to be at a classical mechanics physics level by the time I get to my institution, so I can continue my research with my professor. Let me continue with these are the problems I was doing. Last night. So I kind of want to continue these for like 30-ish minutes, and then I'll probably stop. Or I might stop streaming now, low-key, because I'm kind of hungry. I don't know. And because it's algebra based, it's not. Yeah. The magnitude of the displacement. I think this will matter more for like B, C, and D. Okay. I think it's gonna be it. I'll probably watch the lecture sometime tomorrow. I think that's what I'll do. But